Okay. All right. So welcome everyone. This is another Mass MEP edition of our additive webinar series. We are back for application engineering part two or DOS, depending on what language you speak in. And it is Money Talks, building a business case. So this is the third session, and we're going to move beyond the simple technical feasibility to ask the question, is your idea economically viable? So the session will focus on building a business case for additive manufacturing, learning how to evaluate the cost of printing, evaluate make versus buy decisions, and communicate with confidence within your organization to justify the right strategy for using additive manufacturing. So, we are excited to have with us today our two speakers. We have with us Mandy. Is it Moshiri, Mandy? Is that how you pronounce it? Ah, okay. Good, good. I love it. Okay. Mandy Moshiri, she has a PhD. I have to throw that in there because that's extremely important and a lot of work. And she's also a senior research scientist for MIT APT. So APT is Advanced Production Technologies. Oh, see, picking up what you're laying down over here. I can catch all this. Good. And of course, we have with us Hayden Quinlan. He is the Senior Program Manager for MIT APT. And I will introduce our new marketing manager with MassMEP, who is Becky Gendron. So welcome, Becky, as well.
Thanks.
Yeah. So without further ado, I do know that Mandy and Hayden have a lot of great content that we need to get over today, and we only have a small amount of time to do this. So we'll kick it off to you guys, and let's jump into additive manufacturing.
Thank you. Thank you, Haley, for that. And welcome everyone to Application Engineering Part 2 or Part Dos, or if you speak Arabic, Part Ithnain, which
Oh,
that's going to be
Mm,
maybe
mm.
not many people will catch that one. So Haley did the great job of already introducing us, so I can quickly skip over some of the introduction, but just to kind of set the stage for everyone where you are at now in our webinar series is by the end of today, you'll be at the midway point. So this is the third of six. We have a few more coming up, three more coming up. So this first kind of exercise, the first three webinars is focused on getting started with additive, finding good applications. And then today we'll talk a little bit more about how you can justify those applications as good ones from an economics point of view, from a finance point of view. And then the last three webinars are going to be more focused on, okay, you've already made the decision, you're all in on additive, or you're in, maybe not all the way, but to some extent. How do you think about buying equipment, managing installations, those sort of things? So that's really going to get more into the weeds of operating the machine tools. But for now, we're speaking again a little bit at that high level, and we're going to talk a lot about cost and how to calculate the cost of printed parts, get a sense for what is going to be efficient with the funds that you have, and how you allocate money across material, machines, labor, so on and so forth. Not to repeat the introduction, but in case this is your first webinar, just a little bit about us. I've spent 10 years at MIT teaching additive. It's a little bit more than, I think when we started, it was less than 10 years, and now it's more than 10 years. I hit that mark. So been doing this for a little bit of time, to say the least. And then Mandy or Dr. Moshiri here with me, if you want to introduce yourself quickly.
sure. I'm very much below 10 years at MIT. I've just finished 1 year at MIT, but I have 10 years of experience in metal additive manufacturing as a background of materials engineer, and I've been working in the field of metal AM for 10 years now. So from the R&D environment, from the industrial perspective, I've tested all.
It's been a good year, Mandy. It's a 10 years worth of work done in 1 year. Really impressive. So one thing we like to do in these webinars is just quickly recap the previous one. And so I just have a couple of the key sort of summary slides. If you weren't able to join the last webinar, you should watch it. It was great. But in that one, we talked about process, material selection, like picking the right application from a technical point of view. And I've just pulled out two slides. One is sort of a simple diagram, but showing kind of everything we talked through step by step, starting with an application, defining those applications requirements, and then using a requirements-driven understanding of your application to then define your production approach from a material, process technology, even production strategy. Some of the stuff we'll talk about today on whether or not you make it yourself and buy the tools, or whether you work with a contract manufacturer to do that. Really important. I could say a lot more, but this one slide summarizes like every column of the slide where there were 3 or 4 associated slides and longer text. So if that resonates with you, definitely encourage you to check out last month's webinar. And then sort of the top 3 takeaways we had, right, is number 1, knowing when to print, knowing, often in the 3D printing world, they have this cutesy little saying where you say, it's not can you print it, it's should you print it. And there are many things you can print. Some are easy, some are hard, some are really, really, really hard. Some are like dang near impossible and you're pushing the limits of the machine. And then there are a lot of ones that are easy, but don't really make sense for you to print at all because there's a better way to make that part. So that's the first thing is have a deep understanding of whether or not you're printing because you want to take advantage of the printing process. Don't just print to say I wanted to 3D print something. Often that leads to missed expectations and problems down the line. In the middle, we have our, kind of thinking through the iterative loop between as you familiar, I should say it this way, as you get started with additive, you probably won't master the process the first time you press the print button. And so think through the ways that, your design, not just your geometry, but also your process settings and material and so on. Think through ways that you can fail quickly, fail cheaply, develop learnings, cultivate those back into the next, the next print run, and try to be efficient with your time, as well as learn ways to experiment, inexpensively, both in terms of dollars, but also in terms of resources. And then last, I'm kind of duplicating the slide I just mentioned, so not to belabor the point, but thinking about, your additive approach from a very narrow view of requirements and then drawing a production strategy from those requirements, in our experience, leads to more success than just sort of saying, yeah, this is this kind of machine we want. We think it has good capabilities, but we don't know what we're going to do with it, because we have worked with folks in the past who approach things that way. And then they realized 6 months down the line and a couple $100,000 later, wait, we should have gone with a different machine. And you're kind of stuck at that point, and you have to make do. So that can be a painful sticking point. But that said, now we're going to nerd out a little bit, and maybe more than a little bit. And we're going to ask the question of what does it cost to print, and how do we think about the cost of printed parts versus the cost of other manufactured goods in polymers? Maybe those are injection molded, right? In metals, it might be machined or cast components or things of that nature. This is going to be a little academic, and you got to forgive me for that. But there's going to be some formulas, stuff that, you're going to be like, I don't know what I'm looking at here. I'm going to do my best to walk you through it. But part of the reason it's a little academic is we wanted to make these slides something that your estimator or the person providing quotes, right, whatever that person is within your organization, has the ability to build your own internal cost modeling tools. And I can't do that without giving you the formulas and the way that we think about calculating costs. So I'm going to try to balance a little bit of the math. And frankly, it's like arithmetic. It's not hard math, but a little bit of the math with some more practical considerations. That said, if anything starts going over your head or you start falling asleep, please pipe up in the chat, and you can take me back down to earth, where the rest of us live. So to get started, I just want to give a general framework of what do we think about when we think about additive cost? How do we generally compare additive cost to other production technologies? And so you have a very standard cost curve here. So we have unit cost on the y-axis on the left, and we have volume, so number of parts, not like volume of a given part, on the x-axis on the bottom. And this is really old. It's from 2003. But the reason we use this 23-year-old graph is because the cost curve hasn't changed very much. And that has to do with how the process works, and we'll talk about it a little bit. But generally speaking, additive is considered to be competitive with other technologies. In this case, it's only comparing polymers, but the same is true for metals to some extent. at lower production volumes. And you see that there's a huge drop off in part cost for injection molding or other processes. You could say the casting would look very similar. Anything where you have a very steep investment cost in mold tooling or other sort of upfront costs, and then you amortize that very expensive upfront cost over many, many units. That's how manufacturing economics works for injection molding in most bulk, like high throughput production processes. So in additive, we don't really have those high setup costs. We have maybe high operating costs, and we'll talk about that later. But that's where you get the curves that you see here. So the additive cost is treated as nominally flat. Is that the cost of printing one part and the cost of printing the 20,000th part at the end of this graph is roughly the same. And if we were to get into the weeds, it's not exactly that way. There are some economies of scale. It isn't a flat line, but simplifying it to this view is, from a practical point of view, all you need to know is that the more you want to make, the harder it is to justify additive, though that doesn't mean that there are not high volume production use cases of additive. They're just more specialized than lower volume ones. And this is some data taken from Jabil. They would joke and say that they're like the largest company you never heard of, huge contract manufacturer. And again, you can see this is their actual data here, and it's just reiterating the point that I was making, not from 2003, not from an academic publication, but from an actual high volume contract manufacturer. And so when we think about cost, we want to think on a holistic point of view in additive, not just about what does it cost to print our parts, but what is the value that we're introducing to our customers in the use of the additive part? So this is actually a callback to the previous webinar, because in the previous webinar we said print because there's a reason to print. And from an end user point of view, that is often the value that's realized by the customer of the product in use. We can also think about cost and value. So I'm making two arguments here. One is about the customer. Second, internally, operationally, is we also want to think about the value of additive, not just in terms of what it does for our customer, but what it might do for our organization. And so when we compare costs, if for the rest of this webinar, I'm going to talk about the piece part costs, right? Like the bill of materials cost, what you would say this thing in discrete dollars costs us to make. That's often, and there's a particular way to calculate that. But there's also value and cost savings that can be, attained through things like the assembly reduction. So there's an example in the last webinar or previous one of a turbo machinery from General Electric, and taking an assembly that had hundreds of parts and consolidating that down to a small number. I think it was 12 or 15 or something. It was a really impressively small number. And so if we were to add up the cost of 200 parts and then look at the cost of 12 parts, right, we might arrive at one conclusion, which is more expensive, which is less expensive. But the other implications of we have less, we have fewer difficulties due to poor assembly work. We need fewer laborers, right? We could like go from 3 shifts to 2 shifts, et cetera. You want to make sure when you think about additive, you're thinking about all of those value propositions or cost reductions, not just the dollar signs on your part cost. Sorry. And then this is a even more complicated representation that might take you a second to parse through the graph, but basically it's saying that even if my additive part, which is this bottom one here, even if my additive cost increases and it's more expensive to print than it is to produce in a different way, if for my customer's demand for my product is somewhat inelastic, so they want to buy a higher performing good irrespective of the cost. So think about performance applications. So high performance athletes, like in the NFL, we talked about NFL helmets in a previous slide, or performance racing, Formula One, or aerospace. Industries that place a very high premium on performance, we might want to kind of ignore the per part cost, or not ignore it, but we want to think about it in the context of, even if my additive part is more expensive than my injection molded part, If it's better for my customer and my customer is in an industry that's sensitive to performance, maybe that doesn't really matter that it's more expensive because I'm going to make a heck of a lot more money when I sell it at, 2 or 3x the unit price of what my molded part cost. So that's a lot of framing for what does it cost, like how you should think about cost. So we always say cost and value. But now I'm going to tell you how you can calculate the piece part cost of additive parts. So this is going to be a simplified model. It's based on what's called activity-based costing, or ABC, which is a cute acronym because it is a fairly straightforward approach. And basically, the way you treat activity-based costing is you ask the question of what are all the things that cost money, my machine, my material, my workers, etc. Put those into categories, and then you divide the sum total of those costs, right, by things like cycle time or what resources they consume. In the case of additive, it might be how much of the build volume do they consume, right? Treat that as a resource, like the available volume I can make a part in, and then how much volume is one part taking. We also care about throughput and yield as ways to kind of modify those costs, right? So it's like if it takes if I can make 100 parts per build and the build takes, just be simplistic about it, right? 100 seconds. It's nothing in the world works that way, but just to be simplistic, say 100 minutes. So, 1 minute per part. And then if it costs me $100 per build, you see it's $1, $1 per part. So trying to keep the numbers easy for the mental math. That's for me, not for you, the audience. I'm sure you could do more complicated stuff than I can. So hopefully that makes sense at this high level overview. I think it'll make a lot more sense when we dive into the weeds. But basically what I'm saying is we break our costs up into categories, then we allocate those costs on different bases, depending on the activity that's performed and how costs scale within that individual activity. And the general table looks something like this. So I mentioned there's some math, but it's going to be arithmetic, right? It's mostly sums. It's multiplication, division, subtraction, nothing super complicated. But we look at the total cost of a part being what does it cost to get the material? What is the capital? And by capital, we mean capital equipment predominantly, capital expenditure, CapEx. We look at like time and energy, but often time, energy, and information. This is from a famous model called the Ashby model. We're going to group all those for this exercise and just call it overhead to make things a little bit more simplistic. And what he calls time is overhead anyways, but then you have other things. I will say most printing models of printing costs actually just ignore energy. We'll talk about them a little bit, but it becomes so trivial on the cost table. We're talking like 0.2%, 0.5% of total cost, that folks don't go through the effort of calculating it because the effort required, like the human hours to calculate it and put sensors on the machine and whatever else might be more than the actual cost you're paying per kilowatt hour. And then information is R&D and other stuff, which in this case is just sort of out of scope. So we're going to look at all of our costs in these basic categories. And before we get into any of them, one other important concept I have to introduce, sorry, this is going to be very fundamental to a lot of you, but just to make sure everyone's on the same page, is a fixed versus a variable cost. This is showing a curve, again, of injection molding, and it's making that point I was making previously that in injection molding, you have high fixed costs, and then you spread those high fixed costs over the number of units, which is how you arrive at this downward slope of the curve. But a fixed cost is something that you are required to pay, but often we call this a one-time cost, right? Or it's a cost per like a large number of units, and it's unavoidable. But it doesn't necessarily scale, meaning it doesn't increase linearly as the number of units increases. So what would be an example of a fixed cost would be your machine, right? Like you buy the machine once, and then you make however many units you can make until that thing runs ragged and you have to replace it. And in injection molding, that fixed cost would be, say, the cost of the mold. Variable costs are things that you pay incrementally as you increase the number of units that you're manufacturing. So material costs or other consumables, electricity, for example, those are going to be treated typically as variable costs. And this matters for activity-based costing because remember, we want to tally up what does everything cost and we want to allocate it. And so we might do those allocations on a per part basis. We might do them on a per build basis, maybe on a per machine basis. And that sounds like it doesn't really make a big difference. It can actually make a really big difference because you produce different numbers of parts per build, so on and so forth. So with all that preamble, 20 minutes of preamble, sorry, I'm a bit verbose. We will go into an additive model. And in this case, just to reiterate, we're only going to focus on those same cost categories I mentioned previously. If you're deep in the weeds in cost accounting, you might understand what we mean by dedicated versus non-dedicated equipment, but I have to make clear some assumptions that we're going to use one machine tool to make our parts. We're not going to try to calculate fractions of other machine tools. Second is that we're going to treat it as a non-dedicated machine, which means that if we aren't printing the part, it's printing something else. Someone else is paying for that machine time. That's a very important assumption that we're going to make in this webinar, but it's not necessarily one that you should make. It just depends on how your machine runs. And again, going back to the fixed versus variable cost discussion, if a machine is dedicated, meaning it's only making one type of part, if you don't have sufficient demand to utilize that capacity, so if your machine is running 50% of its available capacity, you still are paying the annual cost of that machine fully on that 50% capacity, meaning that the cost of the machine is twice what it could be if the machine were being used at 100% capacity. This is going to be, I'm sorry, I'm like confusing myself, even though it's making sense. So I apologize if the numbers are get a little bit out of sorts. And then, like I said, we're going to ignore some other costs of like design, part qualification, et cetera. Some of those things that we just are going to group into like this generalized overhead metric. So when we look at cost, we at MIT have a cost model, and I'm not going to go through every parameter in the cell, but I'm showing you this because this is something I want you to use if you want to use it. So if you're interested in actually seeing how we at MIT have come up with a model to calculate cost, and you might want to adapt it for your own purposes, we'll be very happy to share this model with you. And it's going to incorporate everything I'm about to talk about, where I show you a formula on your screen. That's in the back end of this Excel worksheet. So send us an email to apt@mit.edu, or me personally, or to MassMEP, and they'll get you to us. Doesn't matter how you reach us. But if this is something you want to explore for yourself, you don't just have to make your own model based on the formulas. You can use ours. And so now we're going to get into the weeds of the nitty gritty. So the way the model works and the way that we think about calculating part cost is we try to simplify things a little bit. You can get really, really sophisticated and complicated with your costing. We're not going to do that here. So we're going to treat every machine as basically as a box. And then we're going to break that box up based on the bounding box volume of a part. So if you don't know what a bounding box means, it means you take the maximum dimension in all three dimensions, and then we create a box around that. So in the case of, I'm looking to see if there's like an irregular geometry that I have near me. I got a bottle of hand sanitizer next to me. So the bounding box for this part would go up here over the top and like this, and all this negative space would still be treated as volume that's consumed by the part inside of the build. So these formulas are just saying, how do we calculate the number of builds necessary to do a production run? And the first answer is that we divide the total build volume by the part volume to allow us to get an estimate for the number of parts per build. And then if we have that estimate, right, we can then divide the total number of parts that we need by the parts per build, and that lets us get to the answer of how many jobs we actually need. This is useful not just for costing, it's also useful for capacity planning and understanding what is the size of an order that you can realistically take before you have to buy a new machine. And that breakpoint really does matter. I worked previously for a contract manufacturer, and we had one potential customer, didn't actually pursue this because while the numbers looked great, the number of parts they wanted us to print was amazing. I was in sales. I would have hit my bonus right away. I was like, let's do it. And then we looked at the capacity and we're like, wait a minute, we would have to get like twice as many machines in order to make their production targets work. So, this does really make a pretty big difference. And so now let's jump into how we calculate those different costs. So for material cost, predominantly what we're thinking about is straight up what is the dollar per kilogram, dollar per pound, however you express it, dollar per cubic centimeter or inch, all different flavors of expressing material cost. What does that stuff cost us to use in the first place? But we don't just want to think about that from a part volume point of view, because the material consumption in additive is not just the volume of the part that's being produced. It's also the volume of the support material that's being produced. And you see the examples on the right where you have the same part printed twice. Well, it's not exactly the same. Geometry is different, but the function is the same. It's like two versions of a design. Where the one on the left you see has quite a bit of support material. The one on the right has almost none. And so when it comes to optimizing your cost and additive, and something that actually I want to talk a lot about in this webinar is how do you save money at each step of the road? You want to think about the cost not just of your pieces, but the sacrificial material that's going to be used. And so that's that first formula, right? Material cost per part is the cost of part plus support. But then the second formula is getting a little bit more complicated because it's saying, hey, wait a second, there's other material loss in the process. And this example is a laser powder bed fusion one, which is a very particular type of material loss, which is called spatter and other effects that as you have a melt pool, some of the particles, even though they are not melted in the melt pool per se, and they don't make up, constitute your part, they get damaged in some way. And that damage means that those powder particles can't be reused. And this is not a trivial number of particles. This is a single digit percent of your build. And when the material can cost $200 per kilogram, right, a single digit percent can actually add up. So in this case, we say we also want to account for material losses in the process. But in that case, so now getting into the fixed versus variable cost discussion, right? The cost per part, the material cost per part in the first equation, this one up here, that one is a variable cost. That scales with the number of parts. Material losses we can expect, maybe not expect, but for this example, we can treat fairly simplistically and say X% of our total powder volume, or whatever the feedstock is going to be lost per print. We could treat it simplistically that way. But if I'm making 10 parts or I'm making 100 parts in that build, if I'm using the same volume, I'm losing that 5% either way. So that cost we treat as not per se a fixed cost, but one that needs to be amortized over the number of parts in the build, which is why you see this more complicated formula on the bottom. And that's how we get to our total material cost on a per part basis. Now, to get out of the math, let me give you some practical concerns, right? How do we optimize our material cost and additive? And first things first, what we need to understand is the OEM stuff is always way more expensive. By OEM, I mean printer. I don't mean the material OEM, because rarely are those the same. Sometimes they are, but rarely that's true. The printer OEM is going to say, buy the materials from us. They're really, they're good. They're just going to work. We have all the parameters developed, and to a certain extent, that's true. However, they're going to be a heck of a lot more expensive. So on the right, I have an example. Now, I've picked pretty much the most extreme example for this. I don't want to give you a sense that every printer and material class works like this. And also, these are slightly different polymer chemistries. So if anyone from Stratasys is watching and says, hey, wait a minute, it's better ABS. Yeah, you're right. But the Stratasys filament, so again, ABS, very common thermoplastic, was what Lego bricks are made out of. If you buy it from Stratasys to run in a Stratasys machine, it can cost you almost $300 per kilogram. If you buy it from eSun, which is, I think, a Chinese-based filament manufacturer, but generally has a good reputation, right? It's $17 a kilogram. Now, these are running in very different machines. I could put a lot of asterisks on this comparison, and I wouldn't say that it's the case that OEM branded materials will always be 10x what you can buy off the shelf otherwise, but there is usually a pretty significant cost premium. And so that's one thing you want to think about is the machine you're buying and your application, can it support an open system, meaning one that can work with non-OEM branded materials, or is it a closed system, meaning it can only work with the vendor supplied materials, and they will try their best to make it closed, right? They'll be like RFID or type interlock systems that read the spool of filament and won't print unless they read the spool, etc. And so you can get much cheaper material that's non-OEM branded, but then you run the risk of buying lesser quality material. The material performance might not be as good. The material variation might be much higher. So in the case of filament, the diameter of the filament might change because they're using a low-cost extrusion system to make the filament in the first place. In the case of powder, your powder morphology, the shape of the powder, might be less regular. The distribution of powder particles might be less narrow. In some cases, and the vendor will tell you this, like the oxygen content might be different, which if you're making medical parts actually matters a lot. They buy a special type of titanium called extra low oxygen titanium to get better results at the end. And then, like with all things, the more you buy, the better the deal, right? So, bulk purchasing is a huge thing in additive. You're buying 1 ton of ABS versus, in this case, several kilograms. You can expect it would be cheaper than the $17 on the bottom, right? Then you would be getting a great deal. And the other thing here I'll say is that, and there's a little bit of a crossover between material cost and consumable cost. And I'll get to consumable cost in a second. But often there are things you have to spend when you press print that you don't anticipate or the vendor didn't tell you. And so you really want to get a good understanding of what those things are. So for example, on certain types of FDM machines, if you're printing high temperature materials, they have these sacrificial polymer sheets that you print onto. So it's 1 per print. And if I buy those from Stratasys, sorry to pick on you, I just have an account on their web store. It's like roughly $37 per print for this sacrificial sheet. And so going back to the concept I was talking about earlier about how do you save money in additive and think about clever ways to amortize those fixed versus variable costs, right? If I print something the size of a thumbtack, I have to use one of those sheets. If I print something the size of a cinder block, I have to use one of those sheets. So if I want to get the best bang for my buck, and this is going to be true for all additive processes generally, I want to load as many parts into the build as I can reasonably get away with, because there are going to be fixed costs simply with pressing print, irrespective of how much material I'm using, and I want to be optimal in that way. So the next cost category we can go to is machine cost. And this is this formula is a little bit complicated because it's doing 2 things. Number 1 is it's converting the total list price of a machine into an annual cost based on an assumed depreciation schedule. So I'm going to leave that to you all to make decisions on, because actually, how do you depreciate additive equipment is an open question, and it's also not a question academics have thought of, but practitioners think of a lot. Generally, we model what's called straight line depreciation, which if you're an accountant, you know what that means. But it just means that if the thing costs $70,000 and we say it has a useful life of 7 years, then we say the annual cost is $10,000 over that 7-year period. We also overcomplicate this a little bit to calculate the discount rate, which is otherwise called the cost of capital. And so this is like measuring if you have to take a loan from a bank or something, or if you put the money in a bank to accrue interest, what's the price of basically it's like the opportunity cost, if that makes sense, right? Assuming that money is fungible and you have it. I told you it was going to get a little academic. So you have to forgive me. This stuff may or may not matter to you. Honestly, where it matters most is going to be when you're making really expensive machine purchases, because then that 3% interest rate or whatever it is makes a pretty big difference when you're spending $2 million in CapEx. If you're spending $2,000, like I wouldn't even think about this. I probably wouldn't even think about depreciation. I'd say it's $2,000. We're gonna depreciate it immediately in the first year and not worry about it too much. And then, of course, in order to get our hourly cost, I don't just take the $10,000. So go over the previous example, $70K machine cost, 7-year depreciation schedule, straight line. It's not like, oh, my machine costs $10,000, then I divide 10,000 by all the hours in a year. I have to divide that by the number of working hours. And so that's going to be a function of my shift schedule. That'll also be a function of your assumptions on uptime, downtime, planned maintenance, those sort of things. When I mentioned previously that we're going to treat things as non-dedicated equipment, hopefully now that starts to make a little more sense what I mean. Because if a machine is dedicated, that $10,000 per year is up to these whatever number of parts are being printed on that machine. It's up to those parts to absorb that full $10,000, right? And if I made one part, that part would cost $10,000 plus everything else. Whereas if a machine is not dedicated, right, then we can do a generic estimate and say we assume the machine is going to be running for this many hours in a year and calculate the dollar per hour, and then treat things that way, where even if my parts or one product is only taking 50% of the capacity, it's not paying for the other 50%. Some other application is. And then if that other application doesn't exist, suddenly you find yourself, right, $5,000 in the negative, and you're like, wait a minute, what's going on here? So, when you make these modeling assumptions, you do want to have a good handle on what your demand is going to look like, and how realistic it is to treat an instrument as dedicated or non-dedicated. But okay, and then this is just a more complicated formula, but it's just saying like now we want to discretize that on a per part basis. And we're going to do that not just in terms of the amount of time that the machine is printing, but we also want to think about the time that it takes to set up a print. So in some printers, they have to warm up, and then after they're done printing, they got to cool down before you can handle the parts. You might have to exchange build plates or load or unload material. So it's saying we don't just want to think about the printing time per part, which is that over here. We also want to think about all the other time that's required in order to press print. And again, some of those times are going to scale with a number of parts. Like the amount of time, like the printing time will obviously scale linearly with a number of parts, because the machine has to do more to make more part. Whereas the warm-up time, the cool down time, the build exchange time, those might be the same, right? Whether you're printing one tiny part or you're printing, one huge part or 1,000 small parts or whatever, those might be roughly the same. And if they're roughly the same, again, how can we try to be efficient? We are efficient by putting as many parts as possible into each individual build. So how do we think about machine costs? I'm going to give you some other considerations. First is that the printer is rarely the only thing you have to buy from a capital equipment point of view. So on the right, for example, in the top right here, I redacted the name of this company. So, but let's treat a vapor smoothing system. So fumes a solvent vapor on a thermoplastic part that basically chemically melts the exterior of the part, which allows you to get really smooth surface finish. So if you want to print a part in thermoplastic but have it look like an injection molded part, people often do what's called vapor smoothing. The entry-level vapor smoothing unit, like the cheapest one, and actually this quote is $23,000. And this guy quoted it to me because he said, hey, do you guys want to buy one at MIT? And I said, no, man, those are so expensive. The last time you quoted me, it was $100,000. So has it gotten any cheaper? Does it make sense? And he said, oh yeah, I got a lot cheaper. It's 23 grand. A machine, an entry-level machine that you might use this process for is, 29,000 to 57,000. So we're talking about anywhere from almost 100% of the machine price or half in an optional post-processing tool, which depending on what your customer cares about in your application, if they want injection molded like surface finish, you might have to buy. So that's the first thing you want to keep in mind is what's your full printing process chain, not just the printer itself. Second is you got to think about facility costs and renovation costs. This depends on what machine you're buying, right? Again, if it's that $2,000 extrusion machine, your renovation costs are going to be like 20, 30 bucks, right? Like I got to buy a new desk. You're going to buy a rubber mat to keep it from vibrating, simple things. If you're talking about laser powder bed fusion machines to print titanium, then you're talking about overhauling your HVAC system, installing, uninterrupted power supplies. You might, in some cases, they redo the floors entirely to use epoxy, electrostatic dissipating materials. Like you can go overkill. So the way you think about renovation costs is predominantly they're driven by two things. One is safety. That's the number one thing I would argue that increases the cost of an installation. And then second, in my experience, like electrical requirements can come into play, especially when you're using lasers, using a lot of lasers, right? Then you might need to do some things electrically in order to get the right power to the machines that you need. So I'm giving you a very basic rule of thumb. In some cases, it won't apply. It'll be an overestimate. In some cases, it'll be an underestimate. But I would say if you're buying a printer that's like tapping out your budget, and it's really painful for you to ask for more money after you buy the printer, don't buy that model, right? If you can absorb roughly twice the acquisition cost of the machine, you'll probably be able to account for all the incidentals that you didn't think of. Now, I use the word probably, that might not be the case, but generally, I think that's a fairly safe rule of thumb. If anything I say sounds absurd, Mandy, by the way, jump in and intervene if you think that number should be different. But it's just sort of general guidance. The other way you can think about optimizing machine cost is by used, right? Like we buy used cars all the time. So why not buy used printers? And to be honest, there are a lot of really high quality printers available used because the people who bought them didn't really know what they were going to do with them, which is the theme of our last webinar. Don't be that person. Know what you're going to do before you buy. But because they didn't watch that webinar, or for whatever reason, right, they bought a machine. You can buy machines that have a very low number of hours on them. And the way that you think about assessing used machine quality is you want to find like the highest value component that is most likely to fail and cost you a lot of money later on and be very painful. And usually that's how we think about mileage on a machine. As we say, it's like in an LPBF machine where the L stands for laser, people talk about number of laser hours, not number of working hours, because the machine has to, again, heat up, cool down, recoat, do a bunch of other stuff. We say number of laser hours because the laser is the most expensive subcomponent and replacing it is really painful. And if it doesn't work, the machine doesn't work. And so that's how you think about it. So folks have come to us and they said, oh, we have this great machine. It only has 300 laser hours on it or something, which is basically zero in the case of LPBF. 300 laser hours is like, I don't know, 20 builds or something. It's not that much. Whereas if they told me it had, 30,000 laser hours, I'm like, what the heck? You're still using the same one? So that's how you can think about it. And just to give you a sense of the cost savings, right? Like this one here is on the bottom right is from 2022. So a fairly recent unit, right? 4 years old, 40K list price. I don't know exactly if you can buy the same unit today, and you sure can't go on their website and find it. But I can tell you from experience that jetting machines of this type are often more than 100 grand, sometimes up to several hundred grand. So 40K, pretty good deal. And then the other thing, general advice, and I'm kind of talking about things I'll talk about in a later webinar. But of course, you always want to, if you're buying used, even if you're buying new, you want to think about ways to get some quality guarantees there. So don't just be like, oh, I got a screaming deal, let me go for it, right? Think about ways that you can use payment terms or have them do test prints or other things to build confidence that the machine is in the right working order before you commit to the full acquisition price. Next, we have consumables cost. So this is like don't look at the formula here. And I'll just tell you what it means because there's like so many terms in the formula, but it's actually simplistic if I just articulate it to you. There's a bunch of stuff I got to pay for when we press print that is not material and is not machine. So that might be gas. That might be those build sheets I had on the previous slide, right? You could probably more realistically treat those as consumables. Those could be things that wear down. So I just spent time talking about lasers. Well, the laser in a way could be treated as a consumable. So these are going to be things that have to be replaced at some frequency. That frequency might be every build, but don't fall into those other categories. So that's what this is modeling, right? Cost of gas, volume of gas, cost of energy, those sort of things. And I'm going to glance over this quickly, but just to say on the energy side, I said most people don't calculate it. That said, if you are sensitive to your energy consumption, you should know that additive is very energy intensive. So this is modeling the electrical requirements on the y-axis relative to the machine throughput on the x-axis. So down here, the bottom right, right, would be like the sweet spot process. I would say is using the least amount of energy and making the most amount of parts, right? Additive, which if you this is again kind of sort of a complicated graph, but if you look down here, like these circles, the blue and red circle, additive is up here, right? Taking a fairly large amount of energy to produce not that many parts, whereas injection molding, uh, electric induction, I'm actually not familiar with that process, but a few other processes that were more conventional manufacturing processes you see are a lot more energy efficient. So consumable costs, non-trivial. In some cases, consumables can be more than material. So on the top right, we're modeling the cost of a process called cold spray. And that process in particular uses a ridiculous amount of gas, like more than 1,000 liters per minute in some cases of gas. And so the cost of the gas is more than the cost of the material itself that we're printing by a fairly significant margin. The other thing is that oh, I repeated my build sheet. Okay, sorry, I'm using the wrong slides. But in any event, I'm going to repeat the point, I guess. Different machines operate differently. So this build sheet thing that I'm complaining about, $37 per print, some printers don't have them at all. And you have permanent build platforms and build sheets, at which point, you replace them with some frequency every 100 or 200 prints or something, because sometimes you just like degrade them a little bit or scratch them or whatever it is. Other machines have required consumable costs. And so this middle one is really important. Like you really want to know what you're buying. And so you don't just want to look at a spec sheet because this information is not going to be in a spec sheet. And in fact, the vendor might not tell you at all. You want to go and fully understand what is the workflow, what are all the things that are required, what comes with the machine, what do I have to buy separately to get a full sense of the cost of your consumable use. And I would argue that you really want to speak to end users and not the OEM when it comes to getting high quality information. And just like give you a little window in, right? Additive machine sales typically operate under the razor and razor blades model, meaning they sell you one thing at a reasonable, depends on the machine, reasonable price, but then they try to get you with all the extra stuff that you have to buy afterwards, and you have to buy it from them. And so in some cases, right, understand a printer OEM, depending on the machine, their entire, USA division might sell less than 10 machines per year. And if the machine costs less than $100,000, right, that means they're making less than $1 million in revenue per year. And they'll have 5 or 6 employees. So you're like, wait a minute, what's going on here, right? Like, how are you even making money sustaining yourself as a business? And the answer is through the things they're selling after you bought the printer. And so if you can understand that that's where there's going to be the greatest margin for your suppliers, and that's also going to be the place where, frankly, because they have that big margin, you can get creative or in your machine selection and your operational workflow. If you kind of, sort of hack it, right? Find your own cheap polymer sheet and then have someone else cut them to size for you. If anyone's Stratus is watching, I'm not telling people to do that. I'm just saying they could if they wanted to. Those are ways that you're going to be able to get the best bang for your buck because this stuff can really, really add up. And also, it's not going to be very transparent before you buy a machine just how significant those consumable costs are. So, I really strongly recommend that you look into all that stuff in advance. Last but not least, we have our labor cost. Basically, what this modeling is doing is just thinking about all the things that labor is required for. So to exchange builds, to run builds, to prepare jobs, etc. And in this case, we have different types of people, operator versus engineer, and that might make a substantial difference. But labor cost is, again, this is going to be pretty straightforward, right? What does this person cost per hour? So their salary plus their associated benefits and overhead. And how many hours does it take them to do any given task? And that's how we can arrive at what the rough labor cost is. So it's easy to calculate some ways that you can optimize your labor cost in additive. To be honest, there are now, like 5 years ago, I would have said, you got to expect to pay a lot of money for an additive engineer. There's not many of them. They're in high demand. And no, unfortunately, or fortunately for you, but unfortunately for us additive, like industry people, there's a lot of talent out there now, and there's more talent than there are jobs available, right? This in the top right, you see this photo from an annual salary survey at some of the printing industry. For every additive engineering job that gets posted, there's over 150 applicants on average. So finding talent is not going to be difficult, presumably for you. And also depending on what it is, if it's a fairly basic machine, a low cost machine, right? You might get someone straight out of high school that used it in class in high school, has one at home, and like sometimes those kids are brilliant. They know more than me. And I'm always embarrassed when some bright 19-year-old walks into MIT and tells me how to do my job better, and he's right. I would be lying to you if I told you that never happened. So you can find some really talented people. But that said, you want to be very careful with thinking through the right mix of talent for what it is you want the person to do. So I have an example here, which is like, let's assume we're going to use LPBF to make production parts. Seems good. If I want to make firearm suppressors, which happen to just be a very common, like a gun nut, just like a very common use of LPBF. What does that person need to do? Like roughly, they just have to print parts within. This is going to sound basic, right? But they're going to have to print parts within tolerance and keep the machine up and running. Cool. Sounds good. If I want to get the same person using the same type of machine, using a very similar material, say titanium in both cases, but they want to make medical products and they don't want to make suppressors. They have to do all the same stuff as the person before. Make parts within tolerance, service the machine, keep it up and running. But then also they have to be able to interface with your quality management system. They have to be able to create test specimens. They have to understand that are associated with individual builds to enable root cause analysis in the case of a device failure down the line. They have to have a deeper understanding of quality and the determinants of quality, not just from a machine point of view, but from a material point of view. Ideally, they've already gone through this process and understand what's called IQ, OQ, PQ, which I'm not going to get into the details of. You talk to MassMEP about it if you want to make medical parts. There's a lot more knowledge that's going to need to be baked into that person. So when you want to find good labor, it's not hard to find, but finding specific labor for your intended use of additive, I would argue, can be very important. The other thing you want to think about and we break it out in our model. So going back to the slide, you see we have the cost of an operator and the cost of an engineer. It is often the case that design for additive, so designing the geometry, designing the production process, so the parameter development, and like how fast, like the feeds and speeds, to use a machining term, what those are in the additive context, and the person that services the machine. Those might be three different people. At a big company like General Electric, or now they're called Colibrium, but it used to be General Electric, or Siemens, or something like that, big industrial users of additive, those are three separate people. Because they can specialize in individual roles. In your organization, they might not be separate. And so you also just want to think through, like, you're going to need a very special kind of person who can do all three, who can comment on geometry and tweak geometry in a way that, still is good engineering, but allows the printing process to operate more smoothly. So like a manufacturing engineering type exercise, who understands the printing process from a physics-based point of view and can adjust parameters dynamically to get you good outcomes, and is the kind of person that doesn't get bored dumping powder and getting in a bunny suit and wiping things down with Kim wipes and all the other manual labor that's required to keep the machine up and running. And I wouldn't expect you to be able to find those people off the shelf, so to speak, out in the world, because it's sort of a special type of person. But you might be able to find those people very easily within your own organization. So I do want to say, you can think about hiring externally versus hiring internally. But when you're first getting started with additive, hiring internally makes a lot of sense because often it's someone who's excited to take a step up rather than someone who's a little bit disappointed to take a step down when it comes to like cleaning equipment. And the other thing is prints can take a really long time. So you want people who have stuff to do for their full 8 hour shift. You don't want people who are like, yeah, my job is to run the prints. So I showed up, I pressed print, I twiddled my thumbs, I went on Facebook. Like, not the kind of person you want. Well, and maybe they're great people, but I mean, not the kind of job expectations you want to set out. Uh, and to give you some helpful tips, uh, I've heard a lot of folks say they use machinists often as additive system operators, especially machines that use XYZ gantries and other things like that, with some robotically controlled systems, because toolpaths and CAM programming is very analogous in some ways to additive, and the fact that you have to have toolpath control. And likewise, for metal additive, you have welders who are very good at, like, they understand melt pool dynamics, material oxidation, et cetera. So they might be, better suited to those types of additive processes. And then last, this is okay, not the last slide, sorry. But the other thing, there's a lot of other cost factors I didn't calculate because there's no way to just give you a formula to calculate them, right? But we want to factor in and think about the fact that there's going to be some trial and error, like we talked about last webinar, and that has a cost associated with it. Built process parameters, there are often like out of the box ones that the vendor will give you or like baked into the software. You can make those better. And we've talked to folks who have made them a heck of a lot better, like 1.5 times faster and more. So there's a lot of room to run as you develop more and more, expertise with additive and try more things out. But also there can be sneaky costs that are impossible to give you math for, and you just have to live the experience, but know that you might incur them and have that kind of clear-eyed view to what it means to invest in a new process and get started. And then last is post-processing, which is just to say there's like a million ways you can post-process printed parts. It depends on your customer requirements. But again, there are going to be cost trade-offs there. There can be throughput trade-offs there. And in some cases, support removal can be really, really manual and really time-consuming. So even if it's not expressed in CapEx or anything else, it might just mean you have dedicated people, and that can add up quickly. So I said most of this already, so I'm not going to repeat this slide, but I want it on your screen. So if you come and watch the recording, this is sort of my summary of the tips and tricks that I mentioned on how you can optimize costs on materials, consumables, machines, and so forth. I do a great job of being really verbose. So, I'm on time, but I did not leave like 40 minutes for questions. I forgot how many slides I had, or the examples. So I'll just say, I'm gonna like just say quickly at the beginning of the lecture, I talked about cost and value. We have some examples I'll be happy to share with you. Again, if you're interested in the cost model, or what some of these examples look like, how you built that business case. We have some examples where we calculated the cost of what would an additive intervention look like relative to a conventional intervention. This is modeling the cost of molding, the cost of a cycle time reduction for an assembly aid, and an aircraft. This one has a bunch more arithmetic associated with it because you have to calculate fuel consumption and everything. But just to say that the way that you think about building the business case, we need to spend all that time calculating part cost, but then we also want to say, what's it going to do to our operations? And then use a little bit of different math to make the argument that it's going to be more operationally efficient versus the conventional approach that we took. And we can make some really simple models that prove that. And that's what these are doing. They're saying if we reduce cycle time by a certain percentage point, even if we pay a premium for an additive part, that premium can very quickly justify itself by the value in use. And that's true for all these analogies here. And this one, the airplane one, took me a while to figure out. So anyways, I will end the slides here. And I'm happy to answer any questions anyone has. I know we have 1 minute. I'm happy to stay on like a little bit extra if needed.
Hayden, this is great. Thanks for tying MassMEP into that a little bit too. We love seeing some lean processes in there at the end. That was pretty good we love to know that there's always some math that goes into the back end of things because I'll say that's one of our specialties. I don't know if everybody in this organization would agree with me, but I think it is a pretty valuable piece of what we do to keep people lean. So yeah, this